You've probably heard it a million times. You need more RAM to make your computer faster. But have you ever stopped to ask what RAM really is? Well, it turns out the answer is way more interesting than you might think, because RAM, it actually means two completely different things.
Right, so when we talk about RAM, are we talking about the physical chips you can actually hold in your hand? Or are we talking about this powerful, kind of imaginary machine that's the whole foundation of software design? Which one is it? The answer is, it's both. And today, we're going to dive into each of them. All right, first up, let's talk about the hardware. This is the RAM that most of us know, the actual components living inside our computers. Okay, so the most important thing to get is that physical RAM, random access memory, is basically your computer's short-term memory. A great way to think about it is like a workbench. Your hard drive, that's like a giant warehouse with all your tools and materials. Now, you wouldn't work in the warehouse, right? No, you bring what you need to your workbench. That's exactly what RAM does for your CPU. It's incredibly fast, but, and this is key, it's also volatile. Turn the power off, and poof, everything on the workbench is gone. Now, the physical sticks of RAM have changed a lot over the years. Older computers used these things called SIMs, which had a 32-bit path for data. But modern computers? They use DIMMs. That stands for Dual Inline Memory Module, and the key upgrade is a 64-bit data path. That literally doubles the amount of data they can move at the same time. I mean, that's a massive performance boost from what seems like a simple change. And that chase for performance has just been relentless. Starting way back in the late 90s with something called SDRAM, we've just seen this constant march forward. Every single generation of DDR, which stands for double data rate, has gotten faster and more efficient. So let's take a look at how all this speed actually impacts what you experience every day. This brings us to that question everyone asks. Why does adding more RAM actually make your computer feel faster? Well, it's all about avoiding traffic jams, or what we call bottlenecks. So, in a perfect world, your computer has plenty of RAM. When you open a program, its data gets loaded from the slow hard drive into this super fast RAM. From there, your CPU can grab it almost instantly. Everything just feels snappy and responsive. This is what we call the fast lane.
But what happens when you run out of RAM? Well, your computer has to start juggling. To make room for the new stuff, it has to move old data back to the much slower hard drive. And then, when the CPU needs that old data again, it has to sit there and wait for it to be fetched. This constant swapping back and forth creates a huge bottleneck, and that's the lag you feel when your system just slows to a crawl. And just to really appreciate why avoiding that bottleneck is so important, you have to understand the raw speed we're talking about here. A single stick of modern DDR4 RAM can move data at a mind-boggling 34,100 megabytes per second. That incredible speed is the engine that drives that smooth, instant experience we all expect from our tech. So that's the story of physical RAM. It's an amazing piece of engineering for sure, but here's the thing, hardware is only half the picture. To really get how algorithms are designed and measured, to understand how software actually thinks, we need to meet the other RAM. Okay, so let's shift gears now. We're going from the physical world into the purely theoretical. We're now talking about the random access machine. The random access machine isn't something you can buy in a store. It's an idea. Think of it as an abstract, perfect computer that computer scientists use to analyze algorithms. It helps them answer questions like, is this the fastest way to sort a list? Or how much memory will this program need? And it lets them do all that without getting caught up in the messy details of any one specific piece of hardware. Now, to make this abstract idea a little more concrete, let's use a cooking analogy. In the kitchen, you are the CPU, the one executing all the instructions. Your recipe book, that's the algorithm. The drawers where you store all your ingredients, that's your computer's memory, or RAM. And the countertop where you're doing the immediate chopping and mixing, that's a super fast piece of memory called a register. The random access machine is really just a formal, scientific way of describing this whole setup.
So you might be wondering, why bother with an imaginary computer? Why not just test algorithms on a real machine?
Well, the reason is all about objectivity. Real computers are messy, right? They have different processors, different amounts of cache, different memory speeds. An algorithm might run super fast on my laptop and slow on yours. The RAM model creates a level playing field. It lets us measure an algorithm's fundamental efficiency, its time complexity, or how many steps it takes, and its space complexity, how much memory it needs, in a way that's totally universal and hardware independent. The real power of this model is its simplicity. It's built on one core rule called the unit cost assumption. It says every basic instruction, like loading a number, adding two numbers, or storing a result, is assumed to take exactly one single unit of time. This makes analyzing things so much easier. Instead of measuring seconds, you just count the steps. So, for example, imagine searching for a name in a list of 1,000,000 items. One algorithm might check every single name, one by one. That could take 1,000,000 steps. But a smarter algorithm might jump to the middle, see if the name comes before or after, and cut the problem in half over and over. That might only take 20 steps. By just counting the steps, the RAM model proves that the second algorithm is fundamentally, massively better, no matter what computer you run it on.
Okay, so let's bring it all together now. We've got the physical hardware in our machines on one side and this theoretical model for analysis on the other. How do they really stack up against each other?
To really understand where the RAM model fits into the grand scheme of things, it helps to compare it to something even more abstract, the Turing machine. A Turing machine is like the absolute bedrock of computer science theory. It helps us understand what is even possible to compute, but it's incredibly theoretical, really hard to work with. The RAM model is a step closer to reality, which makes it way more practical for analyzing the efficiency of the actual code we use every single day.
And here we have it, the final showdown. Physical RAM is finite. It has different speed tiers like caches, and its purpose is to actually run our programs. The RAM model, on the other hand, assumes infinite memory, assumes every single memory access takes the exact same amount of time, and its purpose is purely for analysis. One is messy reality, the other is the powerful, clean abstraction we use to make sense of that reality.
And really, the key thing to take away is this. The RAM model is not a real computer, but its value is just immense. It's like a powerful microscope that lets software engineers design the efficient, fast, scalable code that pretty much runs our entire world. Which leaves us with one last thought. We started this whole journey talking about how more physical RAM makes your computer faster. But we've also seen how the design of the software, analyzed with that theoretical RAM model, is just as critical. So what do you think matters more for ultimate speed? Is it the raw power of the hardware, or is it the elegance of the algorithm? The truth is, it's the dance between these two worlds that truly defines modern computing.